Hi, I'm Ethan Fish, and this is my challenge assessment 3. I'm going to start out with some goals here that we have for this scenario problem. First, we're going to justify and simplify the heat conduction equation. Then we're going to identify some boundary conditions. Then we're going to make the equation for the temperature distribution. We're going to graph the temperature distribution as a function of Q dot. We're going to adjust and analyze 3 parameters to see their effects on the wire. Then we're going to make a little redesign, or what would be done as a redesign to improve this scenario. Here we go. Here's the scenario that I chose. It's summed up. It's a wire used to heat water by convection. As you can see, that the wire acts as resistance heater, which then goes into the surrounding atmosphere, which is the water. The wire uses electric current to generate heat, which is uniform, as you can read through the scenario. Okay. Here are some of the calculations and equations that were used to analyze this wire. First, in the top left, you can see the assumptions that were made. Heat transfer is steady state. It's one-dimensional because it's moving along the wire one-dimensionally one way. It's not moving in different directions. Thermal conductivity is constant throughout the whole wire, and heat generation is uniform throughout the whole wire. First, right next below that, below assumptions, you can see the heat conduction equation for a cylinder, and that is simplified out throughout multiple steps of analysis of this equation to get the steps that we needed. And we also have it over here for the outer surface. Then on the right-hand side, you can see that there are 2 boundary conditions for this wire. Boundary condition at R equals 0, and it's solved out there, and then you see C1 equals 0. Then our second boundary condition at R equals R naught, RO, or 0. Then with these boundary conditions, you input these equations. You're able to get these equations, and we will simplify them down. So you can see the steps taken to simplify to find temperature, because we were looking to find the temperature at the center of that wire to find the temperature distribution through this wire. So you can see down here in the bottom, we have temperature at R0, R naught, which would be the center line of this wire. Through this calculation here, we can input data that was found in the scenario that you saw slide before this to find it's 125 degrees Celsius at the center of this wire. Jumping ahead there. Here's a couple tables and a graph, so you'll visualize what happened when we modified some parameters. So up in the top left here are the 3 parameters that I chose to modify to kind of see what they did with the graph, which was the temperature through the center line as a function of Q dot. So you can see we modified RO, which is the radius of the wire, K, which is the thermal conductivity, and then T infinity, which is the temperature going to the water that's the surrounding. And then table down here, it shows the original Q dot. As you can see in the graph on the right hand side, that's the bottom layers. That's just kind of the function of this heat transfer. That did not change with the modified parameters up here. But what did change was the temperature there, because these parameters are all inputted to find the temperature in the center line. So as you can see here, we increased the diameter, or the radius, which would increase the diameter as well. We used material with a much higher thermal conductivity, and we increased T infinity 20 degrees Celsius. So as you can see over here in the graph, what these effects kind of were. The orange dots, which is the lower line here, was the original parameters, and then the green dots, which is above, are the altered parameters. As you can see with T infinity, starting out higher, that's what bumped up the initial temperature, temperature there. The radius was, the modified radius allowed for more higher temperatures to be found at these different Q dots, more area to work with. And the conductivity showed a smaller conductivity allowed for lower temperatures because the resistance was just not as high. And with the higher temperatures, that means there's more resistance, more heat generation is involved. Okay, so here we go to some improvements that I thought of for this wire design, to what I thought would be to increase in the radius of the wire will allow the temperature to be substantially higher through the center of the wire. And then the heat generation at a higher starting temperature would be beneficial because then it allows for more variation in the wires that you use, so for cost and whatnot. And then the specific material with the smaller thermal conductivity would give it a higher resistance to allow for more heat to the water. Thank you.